Welcome back to Meaning from Data, Statistics Made Clear. In this lecture, we'll discuss two statistical issues that arise from the social sciences. One of them is a statistical technique that's called factor analysis. And it's a technique by which a statistical model of a complex situation leads to underlying conceptual organization of the phenomenon that we're discussing. The second item is that some social scientists feel that there's an over-reliance on a rather formulaic application of hypothesis testing to their field. So in the second part of the lecture, we'll discuss the Bayesian view of statistical reasoning, which in some sense presents an alternative take on hypothesis testing, and a different view of how we can look at the world and how statistical evidence changes our mind about what the world seems like. But we'll begin with factor analysis. So factor analysis is a statistical technique that tries to find whether data comprising a number of variables can be summarized or explained by a small number of factors. And additionally, we can get insight about the field by interpreting these factors, which come about in a mathematical way, that we can interpret them as explanatory concepts. And we'll see examples of that to see what we mean. So factor analysis is a way of creating concepts. And it creates concepts that sometimes can be helpful in the description or analysis of phenomena in the social sciences. It was Charles Spearman who's credited with inventing the technique of factor analysis about 100 years ago. He was studying intelligence, and he hypothesized that there was one underlying factor of general intelligence. He called it the G factor, that would underline the results of all sorts of different measures of mathematical and verbal skills. The term factor analysis was actually introduced by Thurstone in 1931. The assumption that underlies factor analysis is that there's a small group of latent factors that account for the correlation among a much larger group of observed variables. And I know this is very abstract now, and we'll bring it down to some examples in a minute. But let's think of an example. Suppose you have a questionnaire, and you're given a questionnaire, maybe it asks 50 questions about emotions, say. And each answer has some numerical value. So a question might be, how much fear are you feeling? Or how much control are you feeling? That kind of question. Well, each person who's surveyed is then, after the results are gotten, each person, it has 50 numbers that represent the results of that individual. So there are 50 observed variables. And if you give this instrument to thousands or more people, then you have these 50 variables from each person. So the results for any two of the questions may be correlated to each other. That is, in the population, you may find that most of the people who answer question number 3 with a strong positive answer will also answer question number 17 with a strong positive answer. So, for example, it may be that having more fear may somewhat correlate with having less control. See? They're correlated to each other. So factor analysis is a way of looking for these underlying factors and measuring how much of the variation of the observations, that is the survey results from all the people in the population, how much of the variation is explained by focusing on just these factors. Now, a factor is not just, say, one question or another question, although it could be that, but a factor generally is a linear combination of the answers to a collection of the observed variables. So what I mean by that is that you might have, for example, a factor be the answer to the fear question minus 2 times the answer to the control question. And that combination would be a factor. Generally speaking, if we're talking about 50 things, it would be a factor would include many many combination involving many of the answers to many of the questions, maybe 20, 30 of the questions, or maybe all 50 of the questions. So a person's value for each factor is computable from the values that that person answered from the original variables. One of the features that you want from a factor analysis is that the different factors should be uncorrelated with each other. In other words, if you isolate a factor that is capturing some aspect of that personality, you want the other factors to vary independently over the population. So in particular, we don't want any correlation between the answers to the one factor, the computed factor of one of the factors, and the computation of another factor. So they're like the x and y axis in a graph. If you change the x value, you don't necessarily change the y value. The goal is to find independent characteristics of a person that are being used to describe the phenomenon. So a successful factor analysis would yield a small number of factors that explain a lot of the variation we see in the population about whatever it is that we're discussing, and yet there are just a few factors that explain all of it. And so if you know the values for the factors, you can get a good estimate of the values of the original variables. So that's another characteristic you want. So the goal of factor analysis is to summarize complex data, sort of in a sense analogous to how linear regression was a way of summarizing data. So, okay, let's ground our discussion with an example that will make it maybe more reasonable. So we'll begin by looking at the famous Myers-Briggs personality type indicator. And most of you have probably heard of the Myers-Briggs test. There are over 2 million people a year take this test. And it was created originally to capture Carl Jung's personality type concept. He had a concept of personality types, and the designers of the Myers-Briggs test were trying to capture Jung's concept into this practical form. Now, it's a little bit ironic, by the way, to use something that came from Jung in this lecture on statistics. He has a quote about statistics where he said, "You can prove anything with statistics." So he was not necessarily a great fan of statistics as being the right way to come to insight into human behavior. But nevertheless, the Myers-Briggs test is an instrument that tries to categorize personalities. And here's the way the test works. After you've answered about 100 multiple choice questions, the Myers-Briggs test takes those answers and then presents you with a summary of your personality or preferences along 4 scales. And these scales are the scale of extroversion, introversion, the scale of sensing and intuition, a scale called thinking, feeling, and a scale called judging, perceiving. And the answer that is the output of taking the test is that you get a score for each of these scales. How extroverted or introverted you are, where you are on this line, thinking versus feeling, how you tend to whether think carefully about things or rely on your feeling about them. These are 4 independent axes. So the concept of this instrument is that it summarizes a very complex thing. I mean, the ultimate goal is to summarize your personality type by using just these 4 scales. But in particular, the actual information that it's taking are the answers to these 100 or more questions that are then used to compute your answers on each of these scales. So the point is that these are factors that summarize the much more complicated situation of the answers to all these questions. For example, we have 100 questions, and maybe the questions that are associated with the extroversion, introversion factor would be a combination of the answer to question 1 plus 3 times the answer to question 2 minus 4 times the question 5, and so on. Those are a specific combination of those questions, of the whole 100 questions that you ask, that are combined to put you on that one scale. A good factor analysis has the property that the factors are independent of each other, meaning that if we look at all of the people who take this test, and as I say, 2 million a year have taken this test, so we have lots of data about people who take the test. In order to have a good factor analysis result, what you would want to have is that there's an independence about the extroversion introversion result compared to the sensing intuition result. In other words, if we plotted a scatter plot of people in the population, and for each one we put down their score on the introversion extroversion scale, and then we put down their score on the thinking feeling scale. So you see, every person would have a dot on this scatter plot of these. I've just picked 2 of the 4 factors. And we would find that these results are uncorrelated. That's one of the features of factor analysis, that you would want the results to be uncorrelated, because you want each of the factors to be giving you an independent concept about what it is that you're measuring. The Myers-Briggs test was created, as I said, to capture Carl Jung's concept of personality types. So the Myers-Briggs test, the factors, were not a result of a mathematical analysis, but they have been confirmed by a mathematical analysis. That is to say, they are basically independent, and there isn't correlation among the factors. So they do capture what it is they're trying to capture. But the factor analysis in the case of the Myers-Briggs scale was an after-the-fact concept. On the other hand, sometimes if you can use factor analysis as the way to gain insight about the field under study by first looking at the original variables and combining them into factors that are obtained from a mathematical process, and seeing whether the suite of questions seems to suggest that quality that came from this mathematical analysis really is something of significance in the world. Now, for example, or to give you a little more insight about what the mathematics is involved, if you take all of the factors, all of the variables that you originally measure. In other words, you're given these 100 questions in the Myers-Briggs test. So you actually have 100 different collection of values, and you have a whole population of people who take this test. So you can ask the question for every two questions on the Myers-Briggs, you could ask, to what extent are the answers correlated among the population or not correlated? You see? And so you can make a matrix of a correlation matrix where you have every variable on one side and every variable on the other side, and for every point in that rectangular array, you have a correlation measured, as we've seen before, using the correlation coefficient. You get a number. Well, that is a matrix that operates on a many-dimensional space, and it's a mathematical. The mathematical side of doing this factor analysis is a question of doing some linear algebra that's associated with trying to diagonalize a matrix, and doing some mathematical themes whose effect is to produce this linear combination of the various collections of variables, so that you have one collection that is not correlated to the collection that's representing the next scale that is created by the factor analysis. Well, okay, so let's give an example where the factor analysis itself created an idea. So finding the combinations that give uncorrelated combinations is a mathematical procedure. The mathematical result of factor analysis then sometimes gives insight about the field under study by looking at the original variables that are being combined into the factors and seeing whether that suite of questions that came out from the math seems to suggest a quality that should be identified and explored. So a researcher then would call each factor by some evocative summary name depending on the ingredient variables, trying to say, well, what is that combination capturing? For example, in a study on jealousy, many measures of qualities about jealousy were measured, and people were given survey questions from several surveys, such as an interpersonal jealousy scale and a romantic relationship scale. And from these, 20 variables were extracted from all these surveys. Factor analysis was done on the result, and 3 factors were identified. Well, these factors then are combinations of all of those things that were measured. But the researcher looks at one of those combinations and says, that collection of qualities that are measured by these different questions seems to be capturing something. I'll give it a name. So, in this case, the researcher called one of the factors reactive jealousy, another one anxious suspicion, and another one interpersonal insecurity. And the correlations between each of the 3 factors and the 20 original variables divided the 20 into these 3 groups. That was the point of the factor analysis. But the variables in the first group are highly correlated to the first factor, but have low correlation with the other factors. So in other words, you could have a person who was high on one of these 3 scales and low on the other ones, or high on both. They move independently from each other. So the names of the 3 factors then reflect the researcher's interpretation of the meaning of the underlying factors. So part of the intent that something has been learned about jealousy is that the 3 principal ingredients that underlie the 20 variables somehow explain the concept of jealousy. And so it's identified a psychological feature of people. And of course, care has to be taken in this interpretation, but there is insight that is to be gained about the psychological or social issue that's being studied by seeing what's reflected by the factors that came up from this mathematical analysis. So one of the interesting features of factor analysis is that the statistical and mathematical technique is actually valuable in identifying and isolating new ideas. So in a sense, the mathematics points the researcher in a certain direction, and then the researcher is challenged to see whether that combination of qualities somehow is a core idea in the subject. Well, let's move on to the second topic for this lecture. Einstein once said that mathematics was merely a refinement of common sense. And in fact, that's right. Mathematics and statistics, the strategies of mathematical and statistical strategies, all of these ultimately arise from just looking at the world and taking our common way of interpreting and organizing it, and then refining those methods into some sort of a system. And hypothesis testing that we've talked about it's an example of a strategy for testing features of our world. But actually, in our everyday experience, it suggests that hypothesis testing may not capture all of the common methods by which we evaluate and judge our world. And some social scientists and many others also feel that there's traditionally been too heavy a reliance on hypothesis testing as the way of interpreting evidence. So there's another model that is of progressing toward a clearer understanding of the world that may actually be closer to the way that we actually live our lives. And let me give an example. Suppose we meet somebody and we don't know anything about them at all. Then we're open-minded about what it is that they're like. We don't know where on the scale of honesty they are, how kind they are. But we have a sense that there's a range of what they may be like, but we don't know where they fit on that range. But what happens? Well, as we get to know them, we see them in action, we see them do something, we talk to them, we hear them act, and then what happens? We update our view of what they're probably like. So this idea that we start off with some opinion, or maybe pretty bland opinion, but then we get some data. We see this person being particularly kind, and so we update our probability. We say that person probably is kind, and we see the person doing something else kind, then we say it's more likely that person's kind. And then we see the person do something awful, and then we change our minds again. It's a continuous process of updating our view of what might be. Well, perhaps the best way to understand the distinction between this sort of updating model and the standard hypothesis testing is to look at the following example. So I'm going to give you an example that involves 3 instances in which we do hypothesis testing. And we're going to do 3 experiments, talk about 3 experiments, and statistically speaking, these 3 experiments are identical to each other. In other words, from the point of view of a hypothesis test, they're identical, but my question to you will be, what is our reaction to these 3 experiments? Okay, so here's experiment number 1. There's a person who you are told is an expert, a musicologist. And you do the following experiment. You say, this person's an expert musicologist, so you take 2 pieces of music, one written by Haydn and one written by Mozart, and you hand these pieces of music to the supposed expert, and without saying which is composed by who composed which one, and then the person says which one was composed by Mozart, and then this process is done again. You take another pair of pages of music, one composed by Mozart, one composed by Haydn. You switch them around, you give them to the musicologist. Once again, that person makes a deduction, and you do this 10 times. All 10 times, the person gets it right. Okay? Now, you feel that's your sense about that is that first of all, you're not surprised, and you're pretty confident that this person is in fact able to distinguish Mozart from Haydn. Okay, that's a pretty persuasive experiment. Okay, let's look at another experiment that we actually talked about before, which was the lady tasting tea experiment. In the lady tasting tea experiment, the lady was given 10 pairs of cups of tea, one where the milk had been poured into the tea and one where the tea had been poured into the milk. First milk, then tea. And in each time, she was given a pair of these cups and asked to tell which one was which. And she, in fact, did it all 10 times. She was successful all 10 times. Okay, now we're going to say how we're going to react to this experiment. So I'll give you one more, and then we'll talk about all 3. The third example has exactly the same structure to it. But suppose that a drunk person comes into a bar and says, I can predict the way a coin is going to land. A drunk person, and you say, okay, we'll test it out. We'll do this. You tell me, I'm going to flip the coin in the air, and you tell me how it lands. And so the drunk person, he flips a coin, and he said heads. He said, before it lands, he says heads, and it was heads. And then you do this 10 times. Tails, he gets it right. He got it right 10 times in a row. Well, how do we respond to these 3 scenarios? In the case of the Mozart-Haydn, we're very strongly convinced that that person is indeed able to distinguish Haydn from Mozart. In the case of the lady tasting tea, we may retain a little skepticism. We're pretty persuaded, but still we may have some doubts because we can't really think of what she could possibly be detecting. But in the case of the drunk, it's pretty clear that we still have a lot of skepticism. We know it's going to happen 1 in 1,000 times, roughly, that a person will just by random luck get it right. But we're not really convinced by this experiment that in fact this person can predict the future. We're still skeptical. The point of these experiments is that all 3 of them had the same hypothesis testing structure. The null hypothesis in the first case was that the person could not distinguish Mozart from Haydn. And then the result was significant, had a low p-value. It would happen only 1 out of 1,000 times by luck alone that that person would be able to detect the difference 10 times in a row. Likewise with the lady tasting tea. The null hypothesis was that she could not tell the difference, and yet she could, and therefore we were persuaded. The null hypothesis for the drunk guy, same thing. He couldn't tell the difference, but he got 10 of them right. And yet our response to these is different, and legitimately so. It seems different. Well, the Bayesian point of view is to acknowledge this reality, that this kind of evidence really updates a prior assessment of what we view the world to be. So let me give you an example to illustrate the concept of the Bayesian point of view of the world. Suppose you go into a magic shop, and from the magic shop you select a penny, a coin. It's not a real penny, from the magic shop. And you know it's a magic shop, and you know that the magic shop sells coins that have every different probability of landing heads up. In other words, some of the coins always land heads up. Some of the coins land heads up never land heads up, always tails up, and for every place in between. It's a magic shop. So because we know where this coin came from, we're absolutely agnostic about our predisposition of thinking what the probability of landing heads up that this coin actually has. In other words, our original concept of the probability that the coin will land heads up, by the way, we're assuming that the coin does have some probability associated with it. If you flipped it thousands and thousands of times, some fraction of the time it would land heads up. And that's what we call the probability associated with this particular coin. But when we take this coin out of the magic shop, we don't know. So the picture that we have then is that our a priori concept of the world is that we don't know what the probability of its landing heads will be. It could be anything from 0 to 1. How are we going to change our view of what the probability is? Well, we do some experiments. We simply flip the coin sometimes and take data. So suppose that we flip the coin 4 times, and 3 times the coin lands heads, and 1 time it lands tails. Then, from the Bayesian point of view, we get a new graph about our belief in the probability that the coin is, of what the probability of landing heads is for this particular coin. One thing for sure, since we got 3 heads and 1 tails, we know that it is not a 0 probability coin of getting heads, because we actually got some heads. But let me show you how to read this graph. What this says is that there is some chance that the coin only has a 0.4 chance of landing heads, and yet we got this data. But there's not too much of a chance. On the other hand, there's more of a chance that the probability is higher, and the way to assess this is the following. You say, for every possible probability of the coin, for example, it might be a fair coin, have a 50% chance of landing heads. Under that assumption, we could compute what the probability is of getting 3 heads and 1 tails and 4 flips. And we can mark that probability here. And then, but we notice that if we have a coin whose probability of landing heads is 70%, then it's more apt for us to get 3 heads and 1 tails. And so we compute what that probability is, and we mark it here. So for every possible probability between 0 and 1, we compute what the likelihood would be of the outcome of the experiment if that were the probability. And so our view of the world is that this entire distribution of possible world states is our actual belief system associated with this penny. When we get more data then, what we do is we update our view of the way the world is. When we got an extra tails, it shifted that way. So the Bayesian concept of the world is that we instead of saying the world is exactly one way or it isn't, Instead, we say the world has all ranges of possibilities, like the coin has a range of possible ways that it could be, and what we're updating is our sense of the probability that the world is one way or another. And that experiments then help us to update our probability. This is a little different view of interpretation, but we'll see an example in a later lecture where this comes up. I look forward to seeing you next time.